everyone, and welcome to the Ford-Fulkerson basic algorithm. I'm George Field. So I'm going to tell you a little bit about flow networks first off. So what are flow networks? They are directed weighted graphs where all weights are positive integers. We specially designate nodes as sources and sinks, which are essentially entrances and exits to the network, respectively. We have flow, which is an amount moving through an edge or a path, and we have capacity, which is the maximum flow possible through an edge. Why do we use flow networks? They are useful to model many real-life situations, for example road networks, as we see here, also public transport, sewers, or computer networks, among many other things. So often we want to find the maximum flow, so for example the overall capacity from the source to the sink, and a configuration of paths that achieves this flow. And the Ford-Fulkerson algorithm is designed to find these. So now I'm just going to step through a little example of a simplified version of the algorithm. And first off, we want to create a flow network which represents the problem, and in this case we're going to reuse the example we saw just a second ago. We remove some superfluous edges. We update the labels to show both the current flow and the capacity. And then we start off by trying to add an augmenting path from S to T. Now an augmenting path is a path which adds some flow to the overall flow from S to T. Now in this case we're going to start off by picking this first edge coming out the top of S, and we're then going to go straight to T from that vertex. We update the flow along the edges with the max flow along that path. Now the max flow along a path is determined by the minimum capacity along every edge of that path, which in this case was 7. And we then simply repeat part 3 until no more paths are available. So we can see now that there are no more paths which we can take to improve our flow. But you will notice that we could have taken slightly different approaches and moved some flow around, but we would still come out with the same maximum flow, which in this case is 7 plus 7 plus 25, which is 39. And like I just said, the solution found can be one of many. So just to go over a few extra points, you might reach a suboptimal solution depending on the order that you've selected your path. It seems complete here. Our current max flow is 5, but if you look closely you can clearly see that a better solution is possible. Luckily for us, an augmenting path can push back flow along edges. So this path pushes back flow along that central edge, and in effect this redirects previous paths we've drawn, and this increases our max flow by 2 up to 7. One other thing we can handle is multiple sources and sinks, such as in this example where we have 2 source nodes. All we do is simply add a new master source, and we connect it with edges where the weights are equal to the total output of the original sources. So moving on to the formal algorithm, we're just going to go through a bit of the terminology and the variables used. So first off we have the arguments. It takes a flow network G as well as a source and a sink. We have the flow F, which is actually a function which maps pairs of vertices into a real number. So basically you give it a pair of vertices and it will give you out the flow between them along that edge. And there's a few constraints here. Primarily the flow has to be between 0 and the capacity, and also all of the flow going into a vertex has to equal all of the flow coming out of a vertex, unless it is the source or the sink. So the value of F, which is denoted by these modulus operators around F, gives us the net flow out of S, and it gives us the total flow from S to T. We also have this concept of the residual network, which is denoted GF, which is a capacity-adjusted network for the flow given by F. So on the left here we have a flow network, F, and on the right we have the residual network, and we have its definition in mathematical terms. So we see that what it does is it sets the set of edges, and it updates the values along edges to be equal to the capacity minus the flow. However, if the reverse exists on the original graph, we set the reverse edge to the flow, and this lets us go back as we saw earlier. Now if I move on to the graphical representation, this will become a lot clearer. Here we see the graphical representation of GF, and now you can see much more clearly that we have, in most cases, we have duplicated edges where there is some flow remaining. So in this top left, going from S to this top node, we see that originally it was 4 out of 7, and so we've represented this as 3 going from S to that node, because we've got 3 more which we can push that direction, but we've also added this edge going back with a value of 4 to show that we can push back 4 if necessary. Going back to other definitions, we've got the augmenting path P, which I explained earlier. We also have the residual capacity of P, which is, like I said earlier, it gives you the minimum capacity remaining along the edges along the path, and that will give you the amount that the augmenting path will add to your flow. And finally we've got this idea of augmenting the flow F along P, which essentially means combining two flows together. Here it's defined as F arrow F prime, and F prime is a new flow function where only the edges of the augmenting path have flow, and it's based upon the residual network. So here you'll see F and GF that we featured earlier, but at the bottom on the left here you'll see the augmenting flow network F prime, which features the augmenting path that we're about to add to our network. In the bottom right, we've got F arrow F prime, which is the augmented flow network, and as you can see, this has combined F and F prime into a new flow network, which we'll use in the next step of our algorithm. So let's step through a short example. So we start off by initializing the flow function to 0, so all of the flows should be started at 0. And look for an augmenting path P in the residual network. Here we found one along the top. We then augment the flow F along P, and we can see that the minimum here was 1, so we augment them all by 1. Our new residual network has been updated, so you can see that this top middle edge is now pointing the other direction to show that we can only push back now. And we find a new path. We augment the flow by 2, as that is the minimum. Updated again, and we find a new path. We augment the flow once more. We find another path. We can see that the minimum capacity here is 2, so we augment the flow along this middle section by 2. So we go back and we find one final augmenting path, and we see that it's got a kind of a zigzag shape, and the minimum capacity remaining is 1 on the residual network. So therefore we augment the flow one last time by 1. And now we can clearly see on the residual network that no more paths exist, because if you look at T, there are no more edges going into T. And so therefore the max flow must be the value of F, which in this case is 5 plus 3, which equals 8. To conclude, I'm just going to talk a little bit about the time complexity. So the running time is based on the selection of augmenting paths. Now on the right here is the little example we saw earlier about pushing back. Now this was the path that I first chose, but we can see it would have been a lot quicker if I'd have done the following, which is to just pick the obvious choice of the top 2 first. Now so it turns out that the max running time of Ford-Fulkerson is the order of the size of the max flow times by the number of edges. Now this comes about because each iteration of the algorithm must improve the flow by at least 1. And so it's going to take us max flow steps to get to this max flow. And then each iteration is going to take E number of steps because it has to check every edge to find the path. So Ford-Fulkerson relies on depth first search. Now this causes issues because it may not terminate with irrational capacities because the runtime is based upon the flow. An improvement upon the Ford-Fulkerson algorithm is the Edmonds-Karp algorithm, and it uses breadth first search, which finds shortest paths first. Now this has the benefit that it will terminate with irrational capacities, and it also removes the reliance on the max flow in the runtime. So we now get a new runtime of OVE squared. So thanks for watching, and I hope this was informative. Thank you very much.